Hello and welcome back. I'm still sick, so excuse my coughing. This is the I/O board out of the AMC325, serial number 1210. It has the bad regen in bit. So yeah, I looked at it, ohmed it out, reverse engineered the schematic here, and I thought I'd show you what one of the in bits looks like. So this is it's a pretty simple in bit. We have pin 5 is the regen enable disable line, and it comes in on the DB25. We go through a 220 ohm resistor, which are located in these resistor packs here, and then we've got a 0.1 ohm or 0.1 microfarad capacitor, which are these little blue guys right here. Then we go into a 1N4448 diode, which is these guys right through here. We also have a 4.7K 5-volt pull-up resistor, which are these two packs here, and then we go into a 4106 Schmidt trigger hex inverter, which is located over here, and then that goes right to the micro. That actually makes its way over this 40-pin ribbon, which then plugs into the processor board, which is over here if I had it. Excuse me. So, the way I worked out that schematic, I should probably show you. So essentially how this works is we got 5-volt pull-up here with 4.7K, so that exposes through this diode and through this 220 ohm resistor around 4.7-ish volts, 4.3-ish volts, because we have about a 0.7 volt drop across this diode here, out here. And when you connect that to ground, that pulls the voltage here. We've got the 4.7K going through the diode and through the 220 ohm resistor to ground, and that puts the potential over here to be one diode drop, which is 0.7 volts, which is above or below the threshold for the Schmidt trigger, and it flips. So that gets us, we got a low here, we get a high here. When there's nothing shorting this out, then we just have the 5 volts being pulled up over here, and that makes that high, and you get a low. So it's a pretty simple in-bit. The 220 and the 0.1 are just doing hardware switch debouncing. This is pretty simple. There's not much going on. So that's the schematic. And how I reverse engineered that was pretty simple, because we know we're starting off on pin 5, right? So using our old-fashioned voltmeter here, put in continuity mode. If we come off of pin 5 on the DB25, so they've conveniently got a square for pin 1, 2, 3, 4, and 5. But we see there's no traces around there. So it's routed on the other side, and we can't see because of the connector. But we know it's got to go through those resistors somehow. And the reason I know it needs to go through resistors, because if you look at all the other ones, they all go off to resistor pins, right? All the I/O lines have to go in through here. So we could probably figure out the order, because it is a pretty standard order. But what I did, I just go on to pin 5 here, and we just go and probe everybody until we find out what pin is making contact. So we definitely know it's that pin, and if we look at that trace, we see this via. So they're on the other side of the board, they're going like this over to this via, and then they're coming up to here. Now I also know that this resistor pack is just a bunch of resistors, individuals, so we know these two are going to be resistors. So if we put it on resistor mode, we can measure across here, and we get that 220 ohm resistor, right? So we go to the next guy, we get a 220 ohm resistor. We go to this gun, and we don't. Well, that's kind of odd, because we know that's the one that we're connected to, right? How come that doesn't? Well, what about the next guy? Yeah, he's 220 too. Well, what does that mean? Well, it means that that resistor is actually blown up. And if you were really good, you would have noticed, astute viewers would have noticed something a little odd about this resistor pack. I don't know how well this is going to show up on camera, but if I put it this way, do you note the hole blown in the side of it? Can you see? I don't know if you can see that, but the whole side of the resistor pack has been blown out. Yeah, I don't know how well that shows up on the video, but when I opened up the drive, there was a slight hint of something, you know, burnt electronics smell, and it came from that. So enough current flowed through there that it killed, or it just blew that resistor up completely. So that 220 ohm resistor does not exist anymore. That's why it's an open circuit. So we continue following that along. Well, actually, I'll just do it on this side because it's easier. I'm cheating because I know where all the parts are now because I ohmed it all out. But essentially, you do the same thing. From that other side of the resistor, we end up going over to these diodes. And so if we're back on diode check, and we'll go through and let's see if I can do it this way. Can you still see that? Yeah, you can see that. Okay, so if I go through here and start probing diodes, am I on that? Diode check. Oh, of course, because it's a good diode. See, this is why I shouldn't do things when I'm sick. And the light's backwards. Okay, so we got 0.6 volt drop across that diode. So that's normal. This one we got a 0.6 drop. That's normal. Uh-oh. Yeah, guess what? That's the diode for I/O bit. That's bad. It's a dead short. Next guy. Next guy. So everybody else is good except for that one diode. So if I do it the other way, of course, the diode would block. That was my problem originally. And you can see that that one is a dead short. It doesn't exist anymore. So far on our schematic here, we've blown up the 220 ohm resistor, and we've blown up the diode as a dead short. So the 4.7K resistor is okay. I can't really check the 0.1. I'll go ahead and replace it anyway. So the 4106 pins 3 and 4. So if we go back to ohms, and we're going this hex inverter is straight across. So, but if we just look at the input, which is pin number 3. So if we go to ground, which is always pin 7 here, so we're on ground, and we're going to measure, say, what did I say, it was pin 3, so let's measure pin 2, which is another input. You can see that's nice and open, and measure all these. They got about 5 meg resistance, good high amounts. We go to that guy, 4.7 ohms. Yeah, that's bad. So pin 3 is the input, and it's completely blown. So that's shorted to ground as well. So it looks like what we're going to have to do is replace the resistor pack, the capacitor in here. We'll just replace that to 0.1. I've got a bunch of them. We'll replace the diode, and we'll replace the hex inverter, and we're going to hope that the output of this guy protected and didn't blow up, you know, did not go through the ribbon to the micro. I think it'll be fine because all the other I/O works. Everything else looks fine. It looks like all the damage was contained here. It didn't propagate through, but yeah, that's essentially what's going on. We'll go ahead and swap them out, and hopefully the next video is just this all working fine in the drive. So anyways, hope that was educational, and thanks for watching.